Okay, so there's a theorem. We're going to look at a theorem and its proof, and then we're going to look at a definition. And I want you guys to say we don't understand any of this. So this is from Bartle. We start with the theorem and the proof. Bartle and Sherbert. And it's called Theorem. That is the number that the book gives it, 219. And what it says is that this is one of the statements. There, no smallest positive real number can exist. So can you guys read? That is just terrible, right? Should I fix it or is legible? No smallest positive real number can exist. Okay, and Chris, you've done this before, but now I think we did that maybe with you, maybe, if you remember or not. Okay, so this is just in words. This is what the theorem says is true. And then in mathematics, the language of mathematics, this is how you express this idea in order to verify that this idea is true. So you go, if A is a real number. Okay, questions about this? Kylie, what is this symbol for? I know you just started coming to class, but yeah, so this thing means it's a C with a line across it, means belongs, okay, or in. And what did I say? I said, if A is a real number. So I'm reading it like that. Okay, all right, so if you want to say that you have a number A, this is a number, and you want to say it's a real number, this is how you write it. You go, A is a real number is this symbol right here with an extra line through, right? That's the set of real numbers, which are irrationals and rationals, everything, and their mother is in the set of real numbers. Okay, so if you have this, so theorem says if A is a real number such that, so here is our hypothesis is about to show up. So this is condition 1. And I'm gonna write the second condition. If A is a number such that it is less than a positive number epsilon, and it is greater than or equal to 0. This is our second condition. These two are also this whole thing here. This thing is part of the hypothesis. This is also part of the hypothesis. Another word for that is condition 1 together with condition 2. So we say cond 1 plus condition 2 equals our antecedent. So these things, what is an antecedent? What is an hypothesis? This is what we assume to be true, and on basis of this assumption, of these assumptions, we use these assumptions to prove what's going to come right here, the conclusion that we have to show. So if we have a real number like A, and A is between some positive number epsilon and it is and 0 from the left, it might be equal to 0, but or greater than 0, less than, and this number epsilon is what kind of number? give a hint. We have to know what kind of the epsilon is. So the key thing here is this weird positive number is a kind of a variable for every possible value of epsilon. If this thing we assume to be true, we assume this to be true, then the only conclusion we can have is going to go here. And this is our conclusion or consequent. The consequence of assuming this underlying thing and this underlying thing is going to go here. So let's draw the picture before I start writing out the lines from the book. So we want to have an A that belongs to the real number system. So our picture would be, we have a real number line. And what kind of number is A? It's a positive number, right? Or it could be equal to 0. So if I throw in 0 here, A would probably go here. Or A could be equal to 0. So it's greater than or maybe equal to 0. So it's going to be to the right of it. And if it's never going to pass, it will never go to the left of 0 because A is, by definition, right here. What kind of number is A? Anybody? If it can equal 0 and it's always greater than 0, then we call A a positive number or non-negative number, right? So it's mostly positive, will become non-negative because 0 doesn't have, it's not a positive or a negative. So it's a non-negative number forever. So I could have drawn this, and so, okay, and then what else do I have to do? What's missing from our picture here? Anybody? Vincent? Chris? So I'm trying to, what's missing here? Very good, and here we go. Epsilon better is bigger than and never equal to A. So it's going to go here. So potentially A could have been here, by the way, but I'm not going to do that. Is this a pretty good picture? All right, yes. Actually, so the statement of the theorem doesn't do that. It does actually, sorry, right here. Shit, I keep missing this. Epsilon is always A, thank you. No, yeah, but you have to, whenever you do this, you always do that. Yeah, because, yeah, this is saying that because it's to the right of 0, according to that, but you have to do that. That's just, it's good manners. And I mean, most people know what epsilon is. It's a positive number, just like, but you have to say that. I've never seen a negative epsilon yet. Yes, Ryan wants to say something. Okay, so what Ryan is saying is, since epsilon is going to vary, this is the thing that varies, right? Right now it's over here. It could be a smaller number if it moves towards the left, but it's always going to stay a positive. So you have to indicate that. And the key word here is every. If it was just a number that doesn't changes its position on the real number 9, then we'll be looking at something else. All right. So let's say, folks, is the condition as we have it here, does the picture satisfy the condition? Okay. Let's give Mr. Epsilon a number here. What should we say epsilon equals to right now? Maybe 1. So therefore, this number, this real number, is between 0 and 1. Can epsilon have other values, folks? Math major, Thomas. So let's say it's half, or less than half, 1/3. What if right? We're gonna, because it's for every epsilon, and we drew, and I said, hey, right now I'm saying epsilon is equal to 1, but this condition where a is between epsilon and 0 or equal to 0 better satisfy for every conceivable epsilon we come up with. So Thomas says, let's make epsilon's value equal to 1/3. And so we are saying is the condition satisfied now? It died already. And as soon as, so therefore, in order to fix the situation, we have to move A towards the left. So now I stick it here. Are we good again? So this is the intuitive understanding of what is at stake, because in fact it's proof by contradiction. So you don't even have to do this. Is everything fine now? Can we say that we still haven't got here, right? A seems to be moving towards the value of 0. So what's going to go here is, what is the final value of 0? That satisfies 0. Final value of A for every conceivable epsilon, so that this condition is always true. A when it was sitting here, because we changed the value of epsilon, it failed this condition. Then we moved A here. Now it is okay. But if we make epsilon even smaller, the condition fails again, and so we have to move A. So as we do this over time, A moves to the left. Can it go further left than 0? No. And that is its end place. And therefore, we can say that for this condition to be true, so I'm going to write here, for this to be true for every epsilon, A cannot have any value here other than 0. We have no, and with this value of A, this condition is always true. Let's check this. So we have A equals 0, epsilon is here. All right, so folks, let's do this. Is this a true, does this picture satisfy this condition? Yes, A is to the left of epsilon, and A is greater than, or in this case, equal to 0. All right, if I move, so this was 1. If I make epsilon equals 1/3, is the condition still satisfied? No matter what the value of epsilon is, if A equals 0, this condition will always be true. So, all right, so now let's actually go through the proof. So the proof is by contradiction. And what that means is that we are going to change one of the things, antecedent or consequent. What do we usually change and say that the opposite of what the theorem says? Something here in the hypothesis in the antecedent, or always the consequent? Very good. All right. So we're going to say the opposite of that. Here it says A equals 0. And according to the book, we're going to say A is greater than 0. In other words, if we look at the condition, we get rid of this equality here and then say that, okay, so we're going to do this. So suppose to the contrary, so this is a proof by contradiction. This is our third proof. in this class. To the contrary, that A is greater than 0. In other words, we are saying is that if this condition and this condition is true for every epsilon, then A is in fact, A's value has to be this. So I'm going to write a shorthand version of this. So our new, so this, I'm going to do it in brackets here. Our new theorem statement that we're going to prove is this, that this is the same if this condition is true, it implies that A is greater than 0. This is what we are now trying to prove. Vincent, you good? Yep. Okay. Okay. So suppose on contrary, we chose our conclusion that this will be true if A's value is greater than 0. Let's see if for every epsilon. So the first thing we have to do is test it out for every epsilon. So whatever the value of epsilon, let's just half it, right? If we half how do you say it? Halve, is that a real word? Half it. Half it. How do you say it? Halve. So there's an L and a V or something. This is an impossible word. Okay. So, and I'm going to draw the picture here again. So at this point, what is our line looks like? We have 0, we have epsilon, let's say it's 1, but we don't really, and then A is, let's put A right here. Not in the middle, but right there. So we got epsilon is here, A is right there. And does this satisfy our hypothesis? Is still assumed to be true. This looks good for the hypothesis. Okay, so then we go. But now this time we are saying that A will always be larger than A, never equal to A. And this and so this is we're going to, so what's going to happen when we're trying to show that this thing is true? We'll run into a contradiction. And we're going to run into the contradiction very quickly, like right now. This is the longest proof we'll be doing in this class. So then we have to make sure that this condition assumed to be true is true for every epsilon. And then we say that for an A that is always positive. So we're going to go, then if we take an epsilon equals, and we're giving it this value. So actually, let's put it back right here. So we've come up with a value for how many epsilons do we have right now? We had this epsilon equals 1, and then we're coming up with the second epsilon because this has to be true that A is greater than 0 if this condition is true for, assumed to be true if for every epsilon. So where should we put this new epsilon, folks? Yes, Chris. So if A is all the way to the right here, it's going to be right here, right? So we have our new epsilon sub of 0 equals, all right, what's just happened? What did we break? Which part of the condition did we break? Epsilon, A is always to the, epsilon is always greater than A, and we just broke that. When we assume this to be true. Okay, if we had just said equal to, it would never break, because 0 would be equal to A, and we could keep coming up, just like I showed earlier, with a smaller and smaller epsilon, and this condition would always be true. Any, yes? Kylie, yes? Or K? You going with K or Kylie now? What's your deal? You gotta choose. Okay, and this is our contradiction, because so this part is contradicted, which we've shown that this is not holding anymore, because the assumption assumed to be true does not hold when we assume this. Therefore, and this is the last line, therefore, it is false that A is less than every epsilon for every epsilon. Actually, let me write it like this, greater than 0. So what is this weird state line sentence that the textbook authors wrote? What is he saying? After we do that, we find the epsilon to the left of A, which contradicts this assumption, which is that A better be always to the left of epsilon. When we choose a smaller epsilon, the A ends up being to the right side of that. So this is saying that it is false that A, as in this becomes false, this hypothesis becomes false for every epsilon when we choose this consequent or conclusion. Okay, and we conclude that the original conclusion of the original theorem, and that conclusion was A equals 0, is true, or was always true. Okay. What do you guys think? Yes? Is it convincing, or did I botch this up, unlike last time? Chris, what do you think? Oh. Oh, okay. So that's what you said. Yeah. 0 is not a positive number. And if 0 was a positive number, then there is a real number which is smallest of the positive numbers, which is 0. But in fact, since 0 is not because here's what actually Chris is saying. So that's a good point. All right, so we have 0 here. Let me use red here. I've got 0 here. Let's start at 1. And we are looking at all the real numbers between 0 and 1. So let's find the smallest real number. I'm going with half. And I'm going towards left, towards 0. 0 is assumed to be not a positive number. So therefore, our only choices are any number towards 0 as long as it's not 0. So I'm going left. Was 1 the smallest positive number? No. Our next choice is half. Is there another smallest positive number? Sure, 1/4. Between 1/4 and 0, how many positive real numbers are there? Infinitely many. So let's go all the way here. Is there a number which is smaller than this number that I just chose? Yes, towards the left. And we can keep doing this forever. I could be here for 2 million years, just going left and never getting to 0, looking for the smallest positive real number, because 0 is not considered a positive real number. It's a non-negative number, not a positive real number. It is a real number, by the way. 0 is a real number, but not a positive real number. So in fact, as we hunt and get closer and closer to 0, looking for the smallest positive real number, we keep getting another to the left of our candidate smallest positive real number. To the left of it, another smaller number than the one we just chose. So this would be a forever loop situation. Okay. So what this is in the end is saying is that A is a real number. A does equal 0, but it is not a positive number. Because so this theorem that Chris is pointing out is not saying that 0 is the smallest real number, which I might have just said randomly. A is the smallest, the smallest positive number does not exist. Therefore, if you have this condition, A equals 0, it's the I guess it's the smallest non-negative number, real number, to say that. Okay, all right, so this is the theorem. I thought I was going to do a better job than I did today, but let's move on. Was it okay? Yeah, I wasn't happy with the presentation. Umid, what do you think? Come on, Umid. Okay, all right. Now we're gonna just do a definition, and then I'm gonna let you guys go home so I can go home and eat. The trick is I don't eat. I delay my lunch as long as possible from the morning. It's probably not a good thing for my body, but yeah. Oh, photosynthesis? Oh, the sun. Yeah. Okay, here we go. Now we have been looking at sequences, right? So there's a theorem that we're going to do on Friday. I'll send it via email. It will be a theorem that says a convergent sequence is always bounded. So we're gonna first of all, let's review the idea of being bounded. All right, so let's do this. What is the context of something? What does something have to be in order to be bounded in what we have been looking at? It needs to be a set. So it is a set that is bounded. Okay. What is the sequence of numbers? Even if they're infinite, can also be thought of as a set. If we think of sequence of numbers as a set, then it can be bounded or not bounded. And so the idea is that a convergent sequence. So let's look at this. Let's look at this sequence first. So this is a sequence of real numbers. Let's say 0 is here. We start with, this is our first term of our sequence. Second term goes here, and continues forever. Is this sequence an infinite sequence? Does it have an upper bound? You can, yeah, you can say that, or we can say it doesn't have an upper bound. So this is, I think there's a term for that. Yeah. So it's a divergence because it doesn't have, and it doesn't converge. Now, what if we have this situation? So this is an infinite sequence that I have put into represented it on a number line. I could have also taken these elements and put them in a set notation situation here. And have we run out of time? No. Okay, we got. Okay, good. All right. Now let's do the other one. Here is another infinite sequence. I'm going to put it on the number line, but this time this is an infinite sequence, but it also converges. We've all seen that already, right? So we have A1, A2, let's put 0 here, and then A3. And for convergence, what do we need? For the terms of the sequence to cluster around some limit. So let's limit as in some real number. So let's call it L right here. And then what are we looking for? We're looking for a term after which all the rest of the terms that come after that to infinity will always fall within some epsilon, right? Distance of the limit, right? So A4, and then all the terms better fall within epsilon distance of L. So which term and what index number? Which index number do we use to represent the term after which all the terms only fall within epsilon distance of the limit, which might be an element, a term of the sequence, or might not be? You guys remember? So yeah, so actually I was talking about the last term after which every term. So this term, we represent the index number is uppercase, right? You guys remember the condition? This is the condition. When this is true, when this happens, and n is the right index number, then all the terms after a sub uppercase n will end up here. Or this could also be inside here, but then after that. So, Vincent, tell me, where am I going to put the next term? Because I've got the threshold term right there, the threshold index. Within, right? Here's an, another an. It falls here, 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 goes here, goes here, goes here, but never falls anywhere else. And this is how many terms are there? Infinite terms. So what has happened? This sequence has converged about this number L. So this is a convergent sequence. Okay, so if you have a convergent sequence, then the book says that it is bounded. So the theorem is that, well, that's the theorem we'll prove on Wednesday, but we're looking at the idea. So what is the definition of convergence? I mean, sorry, an upper bound. Right. So we have equal to or less than this. If this is our upper bound, all the terms of the sequence have to be smaller than or equal to m. Okay. So the problem is that gives us what? The bound on the right side. We also want the bound on the left side. And in order to get that, all we have to do is, so what this is saying is, we have a sequence, and let's assume it's this sequence. All the terms of this sequence are less than m. Why is this picture correct? Anybody? How do we test that this m is at the right place? Because all the infinite number of terms are smaller than m. But this just gives us the upper bound. We want the lower bound. So how do we change that? Put the absolute value sign there. And what this is, if you unpack this, all this is saying is an is less than or equal to m or greater than or equal to minus m. Vincent, are these two equivalent statements? Yes. Therefore, we just found our bound here. And what you have actually, and these are not terms of the sequence, what you have is that this sequence is inside this closed set or this closed interval. Is it true that this sequence is found inside this closed interval? If you can show me a closed interval in which all the elements of the sequence reside, you have a sequence that has an upper bound. So on Wednesday, what we'll do is we're going to look at a theorem that says that all convergent sequences have an upper bound, and we'll prove that.